One second. Okay, let me share my screen. Okay, perfect. And we have the practice exam right here. Okay, so I'm gonna also have a recording on my end, just as a backup. All right, so let's get started then. So today we're going to cover a lot of the pipelining questions that are provided here. So for the exam, there's going to be three main topics. There's going to be disk scheduling, like this over here. This is just drawing out the disk drive itself, right? You could think of it almost like a record player with different tracks, and you move along these tracks to find the path to get to all of these over here. I believe that I had another video on that as well, but this one is usually a much easier topic, right? And we also covered RAID as well. RAID is mostly just kind of memorizing the different types of RAID. So I think I also have another video on this. So I'd rather kind of stick mostly with some of the pipelining in the meantime. So before we go into this, let's see. Okay, we got this question. We got the branch predictor question. We have superscalar and multi-programming, multiprocessing. Okay, I think that's a good set to start with, and then we can go from there. So let me move this over, and I'll put this on. Okay, so a couple of different things first, before we go any further, right? We're familiar with the single cycle processor in the sense that we know that if we were to have several instructions, we would have a fetch, decode, exec, mem, write back, and then the next instruction wouldn't start until here, right? Fetch, decode, exec, mem, write back. So this is what we call a single cycle processor. This is what we're used to. In this case, each of these instructions is one cycle, but this is very inefficient because we have to wait till this entire instruction's over before we move to the next one. Now we found MIPS, right? MIPS has a five-staged pipelined processor. So there are two types of pipelines. There's MIPS and non-MIPS. So MIPS allows us, MIPS allows us to have this five stages, which we'll go into, is a way that we can prevent certain hazards from arriving. If it just says a pipelined process without the MIPS, then we know that there would not be any no ops available for that. And we'll go into that in a little bit. So otherwise, right, the main thing to keep in mind is now we can overlap these processes. So instead of doing this right over here, we're going to instead start right after we finish this fetch. Every processor can only handle one fetch, one decode, one exec, one mem, and one write back. We cannot do two fetches at the same time because they use the exact same components at the exact same time. Well, yes, there might be some overlap with the components with some of the other stages. We don't have to worry as much because they use them at different points. So even if, let's say, you're at a restaurant and both you and your friend need the salt, you use the salts first and then they use the salt second. So they can kind of trade off because it's not at the exact same time. It's during the same cycle, but not during the same exact time. So because of that, I can put the next instruction right here. So this allows me to pipeline these guys, and they'll look like a sort of staircase, and on and on and on and on, right? So here we treat our cycles a little bit different. Instead of being the entire instruction, these cycles now look like this. 1, 2, 3, 4, 5, 6, 7, right? Each of these is considered a cycle, right? And when we want to find the CPI, which we'll find later on, right? That's the clock cycles per instruction. We will divide the number of these cycles by the total number of instructions. In this case, this would be 7 divided by 3. Now, not everything works out this nicely, right? We get a couple of different hazards. So going into them a little bit quick, we have 3 types. We have structural hazards, we have data hazards, and we have control hazards. Each of these is for different purposes. We already went through the structural hazard. This is what tells us I can't do 2 fetches at the same time. I have to move it over one. And that's not a problem when I have all loads or all of one type. But what if this was a little bit different now? And instead of this, right? Let's say for my next instruction starting here, fetch to code. Let's say that this was, actually, let me clear this out and we'll start from a fresh example. Okay, so what if we had something like this? Let's say we had an R type, fetch to code exec, and then we know we don't go into memory for an R type, so we go right into write back. Okay, then we do fetch decode exec. Let's say I have a store type, right? Mem. And now let's say I were to have this is not exactly overlapping, but the whole point is, let's say I had 2 instructions that essentially overlapped, right? Let's say that I had a write back instruction and the write backs overlapped for some reason. So actually, I think it would work if I did it the other way around, right? Fetch decode exec mem write back, fetch decode exec write back. Okay, this was the example I was looking for, right? So this is a load type and an R type. Just let's flip it around. So here we have 2 write backs happening at the same time, but this is impossible because we can't do these 2 things at the same time. This is a structural hazard. So to handle a structural hazard, there's a couple of things we can do. By default, the processor will handle this via a stall. And what a stall does is it stalls the entire pipeline. It just skips a stage, just like that. And look, problem solved. The problem is, though, is that it stalls the entire pipeline, meaning the next instruction that I have over here also has to stall here before it can go into its next stage. And likewise, this one here. And likewise, this one here. It's like that one guy who's taking forever on the bus to pay his fare, and you're just like, come on already, you're holding up the whole line. So, unfortunately, that's not always the best way to handle things. But if we have this special hint here that says a MIPS 5-staged pipeline, the key word here is 5 stages, meaning instead of having one of these problem instructions here that only has 4 stages, unless a stall is happening, what if we just make it 5 stages instead? So let's do that. Fetch, decode, exec, but what do I put here? I would put no ops. This is a special operation called no op, aka no operation. Nothing happens. And it's something that the MIPS processor is able to actually process. So instead of stalling the entire pipeline, you're only just pausing here, and everyone else can still go around you. So that person who was very rude on the bus was able to kind of take a step over, wait, and then pay their fare. So other people can still go. And this is fantastic because number one, our problem solved. Number two, look, I don't have to stall here. So the whole line is not held up. Those are the two ways that we deal with a structural hazard. So the key here is if we see that there's two stages overlapping, we ask ourselves, do we have MIPS or do we not have MIPS? If we have MIPS, 5 stages, fantastic. We can do no ops. Otherwise, we're going to have to stall, which can cause some problems later on down the road. Moving on to the next hazard, we have data hazards. Data hazards are a little bit different. This revolves around the actual data, the addresses that we need. So if let's say that I had an R type over here, fetch, decode, exec, write back, right? We could make this no ops write back if we want. That's fine. Let's just pretend that it's MIPS 5 stages. Okay. And then let's say I have a load. And both of these are going to operate on T1. T1 is just some address. We don't really care what it is, but there's an R type and a load type, both that are happening on this one address. All right, cool. So fetch, decode, exec, mem, write back. But we have a problem. Once I start to exec, do I have this updated value? I don't. I don't have this value until I reach write back. Because think about what's going on here. I fetched, I decode, I exec. This is where that ALU operation is happening. We actually do the math. No ops, and then I write it back, right? So this is not written back to this register until the write back stage. Therefore, we have a bit of a dilemma. So, a couple of ways we can handle this. We can simply stall, and we can wait until the write back stage. Now I can exec. I always say you can finally do your exec on the wee. It's like you're going down the slide. You can actually go down. So this tells you that you can actually exec here and then continue on, fetch decode, exec, mem, write back. But you're probably saying, but what if I don't want to stall? This is going to mess up my whole thing because now fetch, stall, decode, stall, fetch, decode, etc., etc., etc. Extremely inefficient. Okay, well, sometimes we have another trick in the question that'll tell us if we can do a fancy thing called full forwarding. This takes advantage of the computer's architecture. This allows us to forward the data from one exec to another. And here's why this works. When we reach decode, we decode our dependencies. We find if we have any dependencies for other registers that are currently on the pipeline. If it's on the pipeline right now, that tells us, okay, we have to stall, or in this case, full forward. Next, when I'm in my exec stage, right, let's say I'm doing the operation. I'm adding 2 to the address, let's say. Okay, cool. What's happening here is that within the CPU's ALU, that's the arithmetic logic unit, right? We're doing the operation. So we do the operation and it gets put in this little temporary register called a Z register. This allows us to essentially have a temporary storage before we actually put it to the address in the write back state. But technically we're on the CPU still. So it's as if someone's walking in the room. They haven't sat down yet, but you're going to take the salts from them or something like that. So they're in the same room as you, but they haven't sat down yet, but you're still going to take it. That's what we're doing here. Write back is when they sit down, but you finish the calculation, you finish with what you're using, And now I can forward this, representing by an arrow, to this exec here. And then just continue. So just like that, we didn't have to stall, we didn't lose a cycle there, and it was extremely efficient. The most important thing is data forwarding can only happen between an R type and anything else, right? So a load, a store, another R type, a branch, or a jump. Any of those other types. But this type that you forward from must be an R type. This is crucial because R type is the only thing that we could take advantage of with this whole finish at exec part. All the other types, they have to still go to their write back stage or whatever their last stage is, right? Load is not done until they get back from memory and put it into write back. The store doesn't even go into the write back, so we need to actually have that go into our main memory first. R type as well, we need to have that in our, we need to have that finished, right? Anything beforehand before we're able to exec. And same with the branch or the jump. We need things done before we're able to do all of these other things. So it has to be R type to anything else. Otherwise, if it was like a load to an R type or a store to a load, anything else, you have to stall. There's no other way to really kind of go around that. Um, and unfortunately, you couldn't do a no ops either because then you end up holding back the line in a sense, because chances are, if one thing needs a data dependency, everything else that follows will also need that data dependency. So it's like someone stops short and everybody collides into that one person. So it's better to just take the L and stall the whole time. Unless, of course, you have your full forwarding and you have the R type that goes to something else. Then by all means, take advantage of it. All right, and the last type of data hazard that we have, the last type of hazard is the control hazard. This is strictly with branches. And this is where we get into the last trick up our sleeves that we have, which is the branch predictor. So with a branch, right, we know that we have fetch, decode, exec. And at this point, we do some operation. We see branch on equal, branch on not equal, whatever it is. We do some ALU operation and jump to wherever we need to go. Great, sounds fun. But sometimes this can cause a problem. If, let's say, we want to branch, if it's equal to, let's say, right? Let's use the example that's given to us over here. We want to branch on not equal to 0. And we're comparing R1, which actually should be T1, this is a typo, and 0, right? Now, T1 is equal to 600. Okay, cool. 600 is not equal to 0, therefore we do the branch. But we don't know to do that until we reach exec, right? Exec is where we actually do this comparison. But when are we supposed to fetch? We should be able to fetch over here. But how am I supposed to fetch something if I don't know that it's there? If I don't have something telling me that I should fetch, I'm just going to wait and just be like, okay, there's nothing else. I've reached the end. There are no more instructions passed here. So I'm going to wait over here. Nothing happens here. I'm going to wait over here. Yeah, the exec's going on, but still nothing yet. At the end of the exec, we wake up and we're like, oh my gosh, I should have fetched something. So I have to fetch over here. Now, because of this, I kind of lost two cycles over here. So I should have been able to fetch over here and decode over here, but because I don't know the result of what I should fetch or not to fetch until the end of exec, I have to wait over here. Likewise, right, the opposite could have happened. What if this was branch on not equal to 0? What if this was branch if it's equal to 0, right? And we know that 600 is definitely not equal to 0. Therefore, we don't do the branch. Now, sometimes we have these things called branch predictors that tell us whether or not to actually take the branch, right? And there's a couple of different types. We have static, which never changes, and dynamic, 1 bit or 2 bit, which always change after every single thing. Think of static as a stopped clock is right twice a day, right? It's stubborn. It's going to always stay at take the branch or don't take the branch. But dynamic 1 bit and 2 bit can learn from this. The problem is 1 bit can flip-flop around, right? So if it tells you, okay, take the branch, and you were supposed to not take the branch, it flip-flops, and now it becomes don't take the branch for the next time around. So this could kind of be very flippant, like it goes back and forth. You don't really have, it doesn't really, it's not really smart about it. And 2-bit branch predictor is a little bit smarter, right? This is the one that cycles through strongly taken, weakly taken, weakly not taken, weakly taken. I'm sorry, strongly not taken, right? So if I start, let's say in weakly taken, and it tells me, okay, I should take the branch. And let's say I'm supposed to take the branch. Great job. You are correct. You get a gold star and you get promoted to strongly taken. Now let's say again, you you're supposed to take the branch and it says take the branch. Wow, great. Loop again. This is like a state automata machine from 320. But now, what if it tells me take the branch, but I'm not supposed to take the branch? I get demoted one. And then what if it happens again? Weekly taken tells me to take the branch, but I'm not supposed to take the branch. Weekly not taken. Now, weekly not taken tells me don't take the branch. And let's say I'm not supposed to take the branch. Go back down to strongly not taken. And strongly not taken, if I'm not supposed to take the branch, loop back around. And again, I can loop between these states as I please. That's what there's an example on the 2-bit branch predictors, right? I highly recommend that you work on that because it really kind of clears up how exactly you go from one state to another state. So anyway, the whole reason that this relates to this is let's say we had this example on branch on not equal. And let's say that my branch predictor was, I'm just going to use 1 bit to simplify this a bit, right? Let's just say it was taken, right? Taken or not taken would be 1 bit. And it says, okay, take the branch. So without a word, when I hear it to code, right, I have to fetch the next instruction. My branch predictor says, yeah, just take the branch. Okay, cool. So I'm just going to start fetching, let's see, exam 3. So I have to start fetching 4 over here. And that's just a load, so fetch, decode. And then at this point, right, I reach my exec on the previous instruction, and I find out exactly what I should have done. So this is going to either verify what I did was correct or realize that it was wrong. Well, in this example, we're saying we branch only on equal, and this is definitely not equal. Therefore, I should not have taken these two instructions. I should not have taken the branch. I have to flush these guys out. So we X them out, and now I can start fetching the next instruction, which there are no instructions left. So that would be the end of that one. If there were, I would start fetching over here and continue onward. That is how we handle control hazards. So if you have a branch predictor, you handle it just like that. If you don't have a branch predictor, you pretend that it doesn't exist and you just keep fetching the next instruction. And sometimes this could result in it not being correct. So not having a branch predictor and saying, don't take the branch, a not taken branch predictor works exactly the same way. And we're going to go through a bunch of these examples today as well. But that's pretty much the gist of all of the hazards that you can find along your way here. So before we get started on the problem, does this make sense to everybody?
Yeah.
Yeah.
Cool. Okay. With that being said, let me get um the template so I could 'cause that has the answer key to it. I just want to have what the actual uh blank diagram would look like. Okay. All right, perfect. So over here, this question has a MIPS five-stage pipeline with full forwarding, and a branch predictor is dynamic 2-bit weakly not taken. So this really combines everything that we've gone through at this point. So let me make my pen a different color, and let's get started with this. So we have a lot of instructions here, but a little hack that can help you save a little bit of time here is knowing that with a lot of Vivek's exams, he usually has the same format. In that, the main branch here, the main control, is being controlled by this branch over here. And this is relying on T1. T1 is being set to 600 up here, and it's only being changed in here. So on previous questions for exam one, you had to keep track of all the registers and all of the mem addresses, and it was a big pain, right? And it wastes a lot of time, especially if you're not going to be using it later on. Well, if you see over here that you're not using T1 anywhere else, I do not have to keep track of any of these addresses. Of course, I still have to put them on the pipeline diagram, but I don't have to say, okay, T5 has mem address 2, T2 has value 2. I don't have to do any of that, which saves a lot of time. Okay, now with that being said, we can get started. So let's start off with instruction 1. Okay, instruction 1 is just a simple load word. So we got ourselves a fetch, decode, exec, mem, write back. Done. Now we have 2. This is a load immediate. So load immediate just works a little bit different in that we don't have a mem stage. We just load a constant, a scalar value. So we fetch, decode, we exec. I do not go into my memory. But given that this is a MIPS processor, I still need my 5 stages. So I do no ops, write back. That's my 2. 3. Load another immediate. Fetch, decode, exec, no ops, write back. Done. 4. Okay, we do another load word. But over here, I see that we have a repeat value. We have a T2 over here. And this is saying get the mem address represented by what's inside T2. So this is just saying we know 0 is in T2. This is just saying mem address 0. But we don't know this until we actually write this back. Meaning, when I decode this, I see there's a dependency. I cannot exec until this write back. Right? So I have to fill in the blank with a stall. So we do fetch, decode, stall, exec, and this is a load, so mem, write back. Okay. So when we have something like this, we just have to be aware of when we have these dependencies. Just want to be clear if that is the case. Oh, wait, I'm sorry. I actually made this mistake the other day too.
Yeah, I was about to say, it shouldn't be data forwarding.
Yeah, I just realized that.
Yeah,
So,
because load immediately is treated like an archetype.
exactly, yes.
Yeah.
Yeah, exactly. So with this, right? I was gonna say, literally did this exact same question, That's why I gotta always practice these questions, do them several times, that way it really gets in. So load immediate, the one beforehand, this is treated as an R-type instruction. And what do we know about R-types instructions? We can data forward. So instead of waiting over here, instead I can do an exec here and I can just simply data forward that. So remember, R-type and load immediate are the same. All right, so in that case, we had for instruction 4, this was just a load word, so we finish off with mem and write back. Awesome. All right, so now we have instruction 5. And 5 is also going to be another R type. I start my fetch, I do my decode. Let's see, any data dependencies. I see one right here, T3. So T3 is a source here, but it's a destination here, meaning this T3 is going to rely on this T3. There's also a T2 here, but notice T2 finished. It's right back over here, so I don't have to worry about that. If I was writing all the data dependencies, of course, I'd still put it down, right? Anything that's within this that depends on a previous value, we always want to make sure that we put down for that. So at this point, I see that I have a data dependency, and this load is not done till over here. But this time it is a load to an R type. This does not let me data forward that. So this one is going to need to have the stall, I believe. Let me put this on the other window so I can actually see it. Yes, this one actually has the stall. So again, right, only if it's an R type or load immediate, because it's the same thing, to something else can I actually data forward this. Otherwise, I got to stall it. And this means that this is going to stall my entire pipeline. So that I actually see this and I don't accidentally put something here, usually I'll put a line or something just to temporarily notify me that there's going to be all stalls here, right? You could also just kind of say stall, 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 etc. That's totally fine too, right? So actually, let's just put a bunch of stalls here, just so we know for a fact that there's going to be some stalling happening, so there won't be anything happening at this cycle for anything below this. So where were we? We were at the add instruction. So we were fetching decode stall. Now I can exec because I'm under the W. Exec on the we go down the slide. And this is an R type, so we do no ops and then write back. 6 now. So 6 is going to be another R type. We fetch stall decode. Do I have data dependencies? T2, but T2 was resolved a while ago. So I don't have to worry about that. Continue. Fetch decode exec. We don't go into mem, so that's no ops and write back. 7, store word. Notice I still have my stall here, so I start fetching here instead. You can put a stall here, that's okay. Technically, it's not really necessary. You'll see kind of on the answer key that it looks kind of as if this is not even here. I personally put it there just so I know that there is a stall happening. I really don't think he would take points off. If you'd rather not have the stall there, that's totally fine. You can totally do that. Just please make sure that you don't start here. You start one cycle over. So instruction 7, fetch, decode. All right, do we have data dependencies? Again, T2, that's old news. We haven't dealt with that in quite some time, so I don't have to worry about that. I don't got to stall that. I just do my fetch decode exec mem no ops. Because again, this is a store, so I stay in my mem. Don't go past that. All right, now we have instruction 8. So instruction 8 is another R type. We are going to do our fetch down here. Fetch decode. All right, do we have a dependency? Yes, we do. T4 depends on the previous instruction, but the previous instruction is a store word, right? So because of this, it works a little bit different in the sense that we're not necessarily going to be data forwarding, right? Because it wouldn't really make sense to do that. But what we can do in this case is we can exec because the last thing that the store is doing is it's storing in mem. Therefore, they leave it in mem. They store the address. They don't need to come back and write it back. I know that I have to go into mem to get that anyway. So at this point, it's done. It's updated, and I can just exec over this. So you can do it on the we or the me, I guess. So now we do fetch decode exec. This is an R type, so we want to do no ops and then write back. 9. Now we do subtract. This is another R type. Fetch, decode. Do we have dependencies? T1 has not been overridden since long ago. So proceed, fetch, decode, exec, no ops, write back. And finally, for this loop at least, 10. This is a branch. Fetch, decode. Okay. This is relying on T1. This is supposed to be a T, not an R. But T1 is being updated over here. But this is an R type, so I can data forward. This will forward this exec to this exec. And now, once I have that, I don't have to stall. I'm good to go. Fetch decode exec, it's a branch, so no ops, no ops. This marks the end of this loop. But remember, we have to branch on not equal to 0. Now, technically, we don't know this until we get to exec over here. So until I get to exec, I don't know if I'm supposed to actually branch or not branch. Gee, too bad there wasn't something that could, tell me if I should branch or not. Oh, look, there is. Okay, it tells me weekly not taken. So don't take the branch. Always good to draw out the little diagram for this guy, right? We know we have strongly taken, weekly not taken, strongly not taken. We are here. I'm sorry, weekly not taken. We are here. Make sure that you read these carefully. All right, so weekly not taken. So this tells me to not take the branch. So I'm going to have this in blue just to tell it apart from where we are, right? So this marks the end of our loop, right? So now at this point, when I decoded this, it's telling me, yeah, this is a branch, but you don't have to take a branch because you have a weekly not taken. So I'm going to sit back and relax. I won't do anything here. I won't do anything here. Oh, you finished execing? Okay, let's do the operation. Branch on not equal to 0. T1, what's T1? 600. Is 600 not equal to 0? Yes, it is. We should have branched. So now I'm scrambling and I have to fetch down here. So I'm going to do my fetch for what instruction? Go back to exam 3, which is all the way up here. That's instruction 4. That is a load word. So we do our fetch, decode. Now it's as if we just pick up where we left off. Decode any dependencies. Sometimes you might have dependencies that loop around, so you have to check. Here is T2, T3. Those haven't been updated in a long time, so I don't have to worry about that. So that's just going to simply be fetch decode exec mem right back, and we know this continues, right? The next instruction, fetch decode, blah, 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 blah. Doesn't really matter. You could just do maybe two instructions. So that's an R type, so might as well just do exec, right? Let's make sure there's any data dependencies. Oh, there is a data dependency, so we should have stalled there, right? So we're kind of just repeating it at this point, right? This is instruction 4, this is instruction 5, so pretty much just the same thing that I have over here. And we know this continues on and on and on and on and on. But for the purposes of this, we don't really need to have that. So how many times is this thing going to run? Well, I know that these two instructions are going to tell me that. Every time I run this loop, I'm going to subtract 1 until it is not equal to 0 anymore. Or, well, it is equal to 0, and you want it to be equal to 0 for it to stop looping. So this is going to run 600 times. So we know that the first time that this runs, I'm at weakly not taken. Tells me don't take the branch. But guess what? The branch predictor was wrong. This means my branch predictor is going to change to become weakly taken. And this is going to be correct for the next loop, right? Because the next loop is going to be 599, which is still not equal to 0. So I do it again, right? I loop again. But the difference is instead of starting over here, I'm going to end up starting over here. So this is going to look like this. Fetch, decode, exec, mem, write back. Fetch, decode, stall, exec, no ops. Wait, I'm sorry. Wait, is that supposed to be that? No ops W. I'm sorry, that's supposed to be a W. Right? So again, this is just 4 and 5. So the very first time our branch predictor will be wrong. Every single time after that, it's going to be correct. Right? And this is going to bring me up again to strongly taken. And it's going to keep going for 599, 98, 97, 96, on and on and on and on and on and on and on until we get all the way down to 0. This is when we're going to end up having a bit of an issue, right? And this is going to end up looking like this, right? Over here, I'm at a strongly taken. I'm on a winning streak. I know I've been right. I'm on a roll. So I'm just going to keep taking that branch. But at this point, this is a value of 0. And 0 is equal to 0, meaning that this is supposed to be false. Oh, well, I don't care. I'm going to still fetch anyway. I'm going to do my fetch. I'm going to do my decode. Okay. Oh, what was that? You said you're finished execing, right? And you realize I was wrong this whole time? Oh, that means that I have to flush these instructions out. So by the time I've reached exec, I have fetched 2 instructions, right? Because I have to wait till the end of exec. So 1 instruction gets fetched here, and 1 instruction gets fetched down here. So I'm not going to continue anymore because now at this point I realize that, oh shoot, I've done the wrong thing. Now I have to flush these guys out, right? So these X's just mean that these guys have been flushed out. So this is what each of these loops is going to look like, right? This is going to be the first loop. This is going to be the second and up loop. And this is going to be the last loop. And the reason I drew out all these different parts is because since this is a dynamic branch predictor, it's going to constantly change things for us. And we have to keep in mind, right? We have to draw it out what happens the very first time you run this, what happens in the general case, and what happens the very last time that you run this, because each of these have different values and different start and stop conditions. And this is going to be extremely important when it comes down to finding our clock cycles per instruction, right? So anyway, this is what this would look like, right? I could change the color a little bit. Oh, actually, that might change oh, I guess I can't change the color right now. Okay, but you can kind of see where this is going. So before we get started on the CPI, so how to kind of decipher all of this, does anybody have any questions?
I have a question. So, what if the branch predictor was actually taken? What would be the scenario then?
Great question. So if it started out as taken, so if we were here instead, we wouldn't have this happening to us over here, right? It would tell us start taking the next branch immediately. So I would just go right to here, right? I would fetch, then decode. I wouldn't just wait to thinking that, oh, I don't have to fetch anything. So because our branch predictor was wrong, that's why we skipped 2 cycles over here. And remember, our branch predictor was wrong again at the very end. That's why we had to flush 2 instructions at the end. So if a branch predictor is wrong, one of 2 things can happen, right? We either skip cycles or we fetch the wrong instructions and we have to flush them later on. Otherwise, we were right for the majority of it. That was these middle cases here. So from the everything that was not the first or the last cycle was correct.
Thank you.
Yeah, of course. Okay. So now, how do we interpret this in terms of clock cycles per instruction? Well, CPI we know is cycles divided by the number of instructions. So let's just write out what our cycles are here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I'm just going to leave it at 20, by the way. I just wanted to get to the end of this over here. So this is going to help us keep track of how many cycles each of these loops runs, because we know that the loop is going to run 600 times, but it's going to result in a different outcome each time. So how do we find out which part is the loop? Well, we know the loop starts at 4 and it goes until 10. I will start by drawing a box, starting at the very first fetch and ending at the next fetch, which let's use this example, the first loop, as our first loop that we'll go over, right? So this is what our loop is going to look like. I'm going to just draw a little box over here, okay? And this is our first loop. So I know that there's always going to be 1, 2, 3 instructions before this loop even begins. So 3 is always going to be factored into it. Now we have 3 different loops to keep in mind. The first loop we know goes until this guy over here gets fetched. So this one's going to be a bit of a longer loop. So let's count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know our first loop is going to be 10. Now we know that it's not going to be 10 all the time because the next loop that we do the fetch isn't over here anymore. It's over here, meaning that now I'm going to have to move this over to here, right? That means this now becomes our box. So basically our box is 2 cycles smaller, right? This is 1, 2, 3, 4, 5, 6, 7, 8. And this case lasts from the second till the second to last, right? So everything between the first and the last is going to have 8 cycles. Okay, so this is going to become plus 8 times. How many times is this thing going to be running? Well, we know that it's running 600 times total. And the first and the last are going to be special cases. So therefore, it's going to have this normal condition, which is when our branch predictor was correct, 598 times. Or actually 590. Yeah, let's stick with that for the time being until we find what our last is going to be. Now, our last, if we notice, is also fetching an instruction here, right? These guys are perfectly in line because it's telling me at this point, I'm still strongly taken. It's telling me still take branch. So that means that we're still going to be stopping at the same place. So this is not going to be 598. This last one is going to function the same exact way that the previous one is going to function. Therefore, this is now going to become 599. So this could always be different. That's why it's very important to look at the first, the middle, and the last. Because this could have been, if it was the opposite way around, maybe the last time told me not to fetch an instruction and I was supposed to actually do an instruction afterward. Maybe there was like an 11th instruction that I was supposed to fetch and I didn't. So because of that, it's very important to go through each of those examples. So we did the first, right? We did the middle and the last. So at this point, right, we know that that part finished right over here, right? This is where our 599th loop ended. Okay, now we need to count our leftovers. Our leftovers, just like how we counted in the beginning over here, 3. We have to count everything past this blue line, right? Because this is where that next fetch would begin. Now, technically, even though we flush out these instructions, there still is a fetch and a decode happening. And these guys are happening at the same time as this over here. So we have to go where the end is, right? So that means that there's still going to be a decode, an exec, a no-ops, and another no-ops. That means past this blue line is going to be 4 more instructions plus 4. Now we have the number of cycles. This whole thing is going to get divided by the number of instructions. Now, how do we find the number of instructions? Well, thankfully, this is a little bit easier, right? We know that these are only going to be the fully executed instructions. So we don't have to worry about any of these guys that were only half executed. We know that our loop runs 600 times, right? And how many instructions are within our loop? 1, 2, 3, 4, 5, 6, 7. So those 700 instructions are going to run 600 times. And how many instructions did I leave out? The ones that are not in the loop. 1, 2, 3. So that becomes 3 plus 600 times 7. And now that becomes our final answer. So these can often be very confusing, right? But we just want to break them down. It helps to draw boxes around them and consider all 3 cases. The first, the middle cases, and the last case, because anything can change all throughout the entire question, right? You've probably seen questions where maybe there was instructions after the branch, or you had to do something completely different. But the key here is if you know what your branch predictor is, you know where the computer is going to tell it to go to. And you know, as a human, you can evaluate it beforehand and know whether or not you were right or wrong. So make sure you go at the pace of the computer because even though you know, hey, I'm not supposed to take that branch, the computer might be like, no, we are taking the branch because that's our branch predictor. So that is how we do these questions. Any questions on your end? Okay. So let's see, what else is part of this question? I see there's a provide, let me go on the, provide the value of the PC at the end of instruction 7 exec stage cycle, right? So we know that we are given the 8-bit system. This is kind of a review from the first exam, right? We know that we have to divide. This is going to say an 8-bit system. So each of these, remember, there's eight bits in a byte, right? So because of this, we are going to have each instruction be exactly four bytes away from each other, right? So because of that, right, we're going to just constantly be adding plus 4 from our offset, which is 2080 in this case. And you can kind of just keep adding and adding and adding and adding until you make it to instruction 7 over here. And it's asked at the end of instruction 7 exec stage cycle. So this is going to just mean that what is the instruction going to be pointing to for the next instruction, right? So we want to make sure that we know with the pipelining, right? Um, what is the PC at the end of instruction 7 exec stage? Well, instruction 7 over here, this is what we're looking at, the exec stage, right? But where do we change our program counter? We change it in the fetch stage. What's happening at the same time as exec? Instruction 9 is being fetched. That means we want to take this one's end program counter value as what we're going to be using, right? And the key here is that this is asking for the end, meaning if it was the beginning, it would just be 9's PC value. But we know at the end, this is when we do our plus 4 bytes. Therefore, this is going to be 9, program counter of 9, plus 4. That means this is pointing to the program counter value of 10. So this is a trick question, right? The reason that this is so tricky is because you think, oh, PC at instruction 7, this is just referring to the PC at 7. And you're calculating it, right? And you're just like, oh, okay, PC 7, that's this guy over here, done. Not really, because we have to remember that things are happening at the same time. Therefore, where is the program counter currently being updated? Well, at the same time as this exec is running, this fetch is going to be running, and this is changing the program counter. Since it's the end, we want to make sure it's the PC of 9 plus 4. If it was the beginning, it would just be the program counter of 9. It would have just been this guy. But since it's the end, 2116 would be our answer for that one. Right? And likewise, the next question is saying, provide the value of the MDR at the end of instruction 3 decode stage cycle. Okay, so this time, this is going to be the end of instruction 3's decode stage. All right, this is instruction 3, and this is their decode. All right, so which of these stages is dealing with the MDR? Well, what we have to take into account is we have ourselves a fetch happening, an exec happening, and a mem happening all at the same time. And we know that we're currently dealing with instruction 3, but instruction 4 is being fetched. And when we get an instruction fetched, right, the MDR is going to fetch that instruction. So while we're doing our decoding, we are fetching 4's instructions. So the MDR is going to have the instruction located at 4. And what's that program counter? 2092. So it's the instruction at 2092. So not the program counter itself, but it's like the MDR has a compass or has like a map app, I guess, and it has this address inputted into its app. And it's telling it, pick up this instruction at this address. And then finally, the last question that was given here is provide the value of the branch predictor at the end of instruction 10 exec stage after the last branch not equal. Well, we kind of did this a little bit, right? We know that the way this is going to work is weakly not taken tells us don't take the branch. First time around, we were wrong. Now we have to go up a level to weakly taken. The second time, we know we're correct because we are supposed to take the branch. That gets us promoted again. And we're just going to constantly stay at strongly not taken because we're going to be correct for another 598 times. Now, at the very last time, we're going to do this and we're going to say, okay, strongly taken, take the branch, whatever. And we're going to realize we should not have taken the branch. We made a mistake. So yeah, we still fetch those values, but we flush them after. Now, even though it is the end, we're still going to bring our branch predictor to weakly taken. We have gone from strongly taken to weakly taken because of that mistake. Therefore, we are ending at weakly taken. So those are three possible ways of kind of assessing your knowledge with these kinds of questions. The main thing to keep in mind with pipelines is there's a lot of stuff happening at the same time. So even if you're talking about one instruction, there's other things happening at the same time. It's like you're taking a class, but there's a bunch of other classes happening at Queens College at the same time. Okay, there's a question. If it asked for the MDR value at the beginning of instruction 3, would the answer then have been the instruction from address 2088? Yes, that was an excellent question. So if the question was asking before, if it was at the end, right? The end over here. So that means that the fetch for instruction 4 has already happened. But what if this was at the very beginning, right? We know that the MDR is not changed until the middle of the fetch instruction. Therefore, that MDR would still have the previous value in it. So it would not have 4's instruction yet. It would have 3's instruction because we haven't changed it yet. So it's very important to pay attention if they're asking at the beginning or at the end of a stage. So definitely try to make sure you're good with that, right? Because again, you see how they try to trick you up, the end of the instruction. I remember I had these on my exam and I got tricked up on them. So always good to pay attention to what's going on and use your pipeline diagram to your benefit. Can you go over that? What specifically?
Oh my God, the 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 MIPS thing, the one where you have.
The this one over here, right? Like when it's
Yeah,
asking
yeah.
like the value of something. Yeah, of course. Okay. So these questions are asking, right? Provide the value of whatever this component is at the beginning or the end of an instructions, um, whatever their stage is at that they're at right now. So there's a bunch of ways that this could be worded. But the main key to keep in mind is, right, we know that we have, right, provide the value of the program counter at the end of whatever instructions given and the stage that's given. So let's break this down one more time. Let's start out with the program counter one. So with the program counter one, we know that we're looking for the end of instruction seven's exec stage cycle. Okay, instruction 7 is over here. Let me change my color again, right? And this is going to be their exec stage. So this is what we're looking at over here. What's happening at the same time is all of this, right? So we know that instruction 9's being fetched, instruction 8's being decoded, instruction 7's being executed, instruction 6 has a no-op, and instruction 5 has a write back. Now, what we want to have is the end of instruction 7's exec stage cycle and what the value of our PC is. Okay, so we know program counter is relevant to our fetch, right? Going back to the first topic that you learned, right? If you need to kind of refresh yourself on this, this would probably be a good time to do that, right? We learned about all of the different stages: fetch, decode, exec, mem, write back, and exactly what's going on in each one. And I'm pretty sure like there might have been questions on exam 1 that kind of also asked similar things to these. But the key here is when we did a single cycle processor, it was a little bit different in the sense that we had only one fetch, one decode, one exec, one mem, one write back happening at the same time. So only one stage was happening at the same time. Here, I could have up to 5 stages happening at the same time. So because of that, right, you're probably thinking, oh, exec, that's not dealing with the program counter. But what's also happening at the same time? This guy's being fetched, instruction 9. So let's go through the beginning and the end because these are very different from each other, right? We know at the beginning, we're given the program counter. And this keeps track of where we need to fetch our instruction from. So we know that instruction 9 is currently at 2112. So our program counter is equal to 2112 at the very beginning. Okay, so I take my program counter, right? If this was asking at the beginning, by the way, we would be done. That's the end. But this is asking at the end. So trace through everything that's been going on, right? So we know we got the program counter, we put it on our MAR, we put it on we have our control wires and the data wires and the address wires. So we put the program counter on the address wire and we send it off, right? We get the instruction, we bring it back to memory, we do all that kind of stuff to it. And then at this point, right, we get that instruction back and we can now change our program counter to the next value. Plus 4, this becomes 2116. So everything else didn't really matter so much, but this does because we're looking at what the program counter is involving itself with. The program counter is now going to be 2116. This means that at the end of this fetch, right, we are now prepping ourselves to fetch the next instruction to 2116, which is instruction 10. So that is how we know that that is our answer for that part. Now for the next part, right, MDR at the end of instruction 3 decode stage cycle. Instruction 3 is here, its decode is over here. All of this is happening at the same time. We have fetch, decode, exec, and mem happening. Which one's dealing with the MDR? Fetches. What's fetch doing? It's fetching instruction 4. What happens with the MDR during our fetch? Well, we know that the MDR is responsible for bringing the instructions data back, right? So we put our program counter on the wire, the address wire. We go into our memory, take the instruction that's located at whatever address it is, right? Instruction 4 is looking at 2092. And now, right, we take that data, we put it onto our data wire, and that has a direct mapping to the MDR in our CPU. That means at the end of this fetch state, that MDR is going to have the instruction located at 2092. So that's the answer for that part. So you want to kind of remember the stuff that you've done for exam 1. And you want to trace through what's happening in this architecture as you're going along. And be super careful on what they're asking. Is it at the beginning or the ends? Because you see how much of a difference it can make. Because program counter is different at the beginning and the end. The MDR could be different at the beginning and the end. It might be the current instruction, the previous instruction, or the next instruction. You don't know. You have to trace through it and pay attention to those things. And that's why you want to use your pipeline diagram to help you out, because now I can clearly see, oh, okay, let's say they asked for some arbitrary instruction. Let's say I was asked instruction 6 decode, right? What else is happening here? A fetch, a decode, an exec, and a write back. Now I can determine, okay, they're asking maybe what about the Z register, right? The Z register is happening at the exec stage, right? So that's when we do the operations in an R-type instruction. Maybe they're asking, what is the Z register at the end of this instruction? So for this, I would see, well, I know that happens at the exec stage. So I look and I know the exec stage is going to be execing whatever the instruction is that I'm looking at, right? Instruction 5. So that's an add type. So it would hold this value, T2 plus T3, since that's what that instruction is holding. That's another example, That's why it's very important and things are cumulative. You want to be really specific and very monitoring of like what is going on here because things can change and you have to keep track of all of these different states at once. Does that kind of clear it up a little bit? Okay, cool. Yeah. These are very trick questions, so definitely try to go through them. Um, Even just trace through kind of what's going on, like in your own head. Like be like, okay, in this cycle, I am looking at this, and I see that there's a fetch happening here and a decode happening here, and just tracing through helps a lot with that. Okay, so let's take a minute And if you can, fill out the feedback form, just because, we're kind of at that midway point towards the end. So if you have just a minute, you could fill out the feedback form. Of course, it's going to be open, so don't worry about that. And please select the December 12th CSCI 212 section. We'll adjust it manually. Yeah, this one hasn't been added, so if you don't see it, don't worry about it. Okay. So with the last half hour, let's try to do a couple more questions. I'm going to skip the branch predictor just because we kind of went through what exactly it's dealing with. All right, data dependencies, right? If you have a question like this, right, we went through data dependencies a little bit, but let's just go through it a little bit more, just to kind of see how to write out something like this, right? So the key to keep in mind here is to know when things are sources and destinations. If the destination is a source for another instruction, we know that we're going to end up having a data dependency. So let me just new tab open here. All right, so we're going to just start with the data dependency part and then go from there, right? So let's see. We have a load word, T1 and T2. Well, it's the first instruction, no data dependencies there. The second instruction, notice we have T1 here. We also had T1 here. This T1 in instruction 2 depends on this T1 in instruction 1. And that's all I would say. T1 in 2 depends on T1 in instruction 1. That's literally it. Okay, now we go to instruction 3. We add T1 and T4 and put it into T7. So this means that now T1 depends on T1 here, and T4 depends on T4 here. So I'll actually make this another color. So here we again have T1 in 3 depends on T1 in 1, and T4 in 3 depends on T4 in 2, right? And likewise, let's just go through the rest really quick. I'm just going to circle them in different colors. I won't write them out. We have over here T7. This is going to rely on this T7. T7 in instruction 4 relies on T7 in instruction 3. Then we have the next part, right? Here we have T4, which is going to rely on T4. And then in instruction 6, we're going to have T7 relies on T7. Now notice 1 and 2 are just scalars. They're just normal numbers. They're not registers. Therefore, they don't have any dependencies on anything else. T1 is not equal to T1 is not equal to the number 1. And T2 is not equal to the number 2. This is what this would look like here. Right, and you would just write it out like, hey, this one depends on this one, and that's pretty much self-explanatory. Okay. Now that we have that part done, we got to calculate the CPI. And we do this by drawing out our pipeline. But we have a bit of a different pipeline this time. This is called a superscalar non-MIPS pipeline. And before we go through this, I want to show you what each of these looks like. A little bit easier if you just kind of see from here, right? There's kind of a lot going on here, right? Now, superscalar has a special component in that I have a I have 4 cores, right? What these are, you could think of your own computer. You probably hear like, oh yeah, you have 8 cores, you have 16 cores, whatever, right? Each of these cores can handle its own instruction. Meaning if I have 4 cores, I have the structure to handle 4 fetches at the same time, 4 decodes at the same time, 4 execs at the same time, 4 mems, 4 writebacks, right? So this is something that can alleviate having structural hazards. And now this is going to look something like this over here. Notice we have 4 fetches happening at the same time, 4 decodes happening at the same time, 4 execs. Now there's a lot of stalls here because 4 times the progress also means 4 times the data dependencies. And this is going to cause us to run into them much quicker. Because before, we would stagger things a lot, right? We know that if instruction 4 needed instruction 1's value, by the time you reach instruction 4's exec, you're probably done with your write back. But in this case, you are absolutely not. You have to stall because this write back is not finished until here. And you're going to keep stalling and stalling and stalling, right? That's why I end up not being able to exec until after I finish this over here. So this is kind of good and bad, right? We're able to do multiple things at the same time, but it can also be very troubling if we have a lot of data dependencies. Now also notice, this is non-MIPS. What did we say about non-MIPS? Non-MIPS, no-ops. MIPS allows us to have the no-ops functionality, meaning that we don't have to deal with stalls as much. There is a lot of stalls going on here because we don't have that no-ops there. And that no-ops is kind of what staggers these things when we have these stages that don't perfectly line up to one another. This one over here is dealing with MIPS 5 stage, right? Now we have no-ops. See, we got no-ops, we got some no-ops and stuff. So ironically, actually, yeah, notice this ends 1 cycle sooner than this one over here. This one takes 12 cycles. This one only takes 11. So having that no-op meant that we got to avoid a stall. And well, yes, we have a lot of stalls here. It still made enough of a difference that we had 1 cycle left. Okay? And then finally, that was superscalar. So what's the opposite of that? You know it. Scalar. This is what you're used to, right? This is just our normal pipeline. This is what we've been doing all night long, right? This is like the same one that we did for the last time, right? And again, we have MIPS, so we have ourselves a no-op. Now, notice that we got less stalls here, but because we staggered this, we ended up taking an extra cycle. This took 13 cycles. So technically, in theory, superscalar should work the best. If I didn't have any stalls, I could be done with 4 instructions in only 5 cycles max. Meaning I could do fetch, decode, exec, mem, write back 4 times and be done with it. But of course, this is not how the real world works, and of course, we're going to end up having data dependencies that slow us down. So in reality, it's not always the best idea. Sometimes it's good to take it slow and steady. So each of these has their own pros and cons in that regard. So with that being said, let's practice on, I think actually there's another, wait, no, that's different. Okay, oh, okay, that's it actually. Yeah, let's practice this real quick then. So the question itself is a four-way superscalar non-MIPS pipelined processor. Okay, so let's try it their way first. Or actually, how about we do it the way we're familiar with? Let's do it our non-superscalar, so just meaning our normal scalar way, right? The way we've been kind of doing it all night long. And we'll work our way from there. Because we have enough time. We could make it through. The last question's not too bad. So, in a case like this, right, we're going to just start off with our ordinary scalar processor. And this is going to be scalar with MIPS. So it's going to be our normal five-stage process. So let's fly through it nice and quick. So we have 1, 2, 3, 4, 5, 6, and there's only 6 instructions. Okay, so we're going to do our load, fetch, decode, exec, mem, write back. No need to worry about data dependencies because there are none. It's the first instruction. Okay, instruction 2. Remember, we offset it over here. So in a case like this, right, fetch, decode, data dependency. Yes, there's a data dependency, right? That's the part in purple that we had, the very first one. So we have to stall. So even though we do have ourselves a no-ops, we're gonna have to stall this because, again, this is giving a data hazard, not a structural hazard. So we stall, fetch, decode, stall. I could exec now because I have the we, and this is still load, so it's going to be mem and write back. Instruction 3, fetch. I'm going to stall, decode. Do I have data dependencies? Yes, I do. I have both 1 and 4. If it was just 1, I'd be done at this point, so I could do it. But I'm not done with T4, since that's at the end of instruction 2. So because of that, I have to stall 1 cycle and then do, I'm sorry, this is R type, so no mem, but we are going to have, wait, I'm sorry, exec, and then no ops write back, right? Because again, this is always going to be 5-stage MIP pipeline. Even though it's kind of redundant at this point because we have the value, what's the point of doing it? We are still going to have ourselves a no ops. All right, then we're going to have over here, remember this is stall, so we do fetch, instruction 4, decode. We have ourselves a data dependency on T7, but we do have an exec here, meaning I can data forward. But, oh, look at that. There was supposed to be a stall up above, so because of that, I have to stall down below. Now I decode, and then I can exec forwards easily. And then this is going to be 4 is store, so fetch, decode, exec, mem, no ops. Okay, then we have 5 is going to be an R type, so this is stall, fetch, decode. Do we have any data dependencies? We do, but T4 finished back in 3, and we have a W here, so I can go, because this is WE, go on the we, and now we have fetch, decode, exec, and this is going to be no ops write back, and this one's just going to be a repeat of that, except we have a data dependency, T7 with T7. T7 was in 4, but that finished over here, so I don't have to worry about that. Fetch, decode, exec, no ops write back. Okay, that is going to be for our for our regular scalar, right? That's what we're used to. Now we want to do superscalar. So superscalar with MIPS and without MIPS are pretty much the same thing. So I'm only going to do one in the essence of time. So I'm just going to split this down the line, and we can make this blue. Okay. So this one was scalar. This is superscalar with 4 cores. And the number of cores is given to you in the question. 4-way. If it was 3-way or 2-way, that's just saying the number of cores that you have, meaning the number of fetches that you could do at one time, the number of instructions that you can handle simultaneously. So if you have 4, that means I could do 4 fetches. If I had 3, I could do 3 fetches, etc. Right? We know most of our computers have way more cores than that, thankfully. So for superscalar, I know that I can have 1, 2, 3, 4 instructions happening at the same time. So I'm going to start out with having 4 fetches, right? And I'm just going to have this as superscalar with MIPS, right? So this is going to involve no ops. All right, cool. So I do fetch, 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 decode, 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 decode. Remember, I don't have problems until I reach decode because decode, we decode our dependencies. So let's now handle it one by one. First one, we know we have no dependencies. It's number 1, no problems. Fetch decode exec, mem, write back. All right, number 2. Number 2 now is going to have one data dependency. It's relying on T1. So I know I have to stall until I reach the W, until I have that we. So now I can do fetch decode exec, mem, write back. Okay, move on to 3. 3 has 2 data dependencies. I'm waiting on T1 and T4. T1 is finished over here, but T4 does not finish till over here. I cannot exec until both of them are done because I depend on both of them, meaning that each of these are going to have to be a stall. Now notice one thing. These are separate cores, meaning that a stall on one does not affect the others. Technically, if 4 did not have a data dependency, I could do an exec right there. Even though it looks like there's a problem because with all these stalls, it looks like there should be another one here. These are on completely different cores. 1 doesn't care what 2's doing, which doesn't care what 3's doing, which doesn't care what 4's doing. It doesn't matter until we have to reuse the cores again. That's going to happen once we realize that we're full and we have to start pipelining our cores again. So let's finish up 4 and then we'll see what that looks like, right? So 4, does 4 have data dependencies? Yes, it depends on T7. Well, T7 is not done until instruction 3 is finished, right? Oh, fetch decode exec, no ops, write back. Okay, so that means I can't exec until way over here. So all of this is going to be stalls. Yeah, it seems a little overkill, but unfortunately that is the way that it goes, right? So now over here, I'm just going to skip a line because at this point, 5 and 6 can't fit at the same time. It's like you're going on a roller coaster and there's only 4 seats. You have to wait until the next car comes that you can get onto. So I have to wait now. This depends on if this is supposed to be pipelined or not pipelined. If this is not pipelined, I have to wait until the end of core 1, meaning I would start fetching over here. Otherwise, right, I would start fetching when core 1 is decoding. So this is just thinking of each core as its own pipeline. So there's 4 of these pipelines happening at the same time. So if I had, right, these guys going, this is just the same as me saying fetch, decode, exec, mem, write back, and me just pipelining each of these guys individually like that, right? Or if this was non-pipelined, then I just have to wait my turn until the whole thing finishes, right? So we're kind of just condensing this into each of these cores. So we could think of this, right, as there is a link between 1 and 5, right? These are both on core 1, and there's a link between 2 and 6. These are both on core 2. And if there was a 7th instruction, that would be linked to 3. they'd both be on core 3. And if there was an eighth instruction, that would be linked to 4. It would be on core 4. And if there were more instructions, you would just repeat that. If there was a ninth instruction, we know that 1, 5, and 9 would all be on core 1. And you could do this on and on and on and on. It's just having 4 separate pipelines. So in this case, we know we have a MIPS. Okay, well, the example I gave was with MIPS. Okay, well, it is a pipeline. So let's just say for this example, I used a MIPS pipeline, right? That means I fetch when these guys are decoding. I can fetch you, right? So instruction 5, fetch, I decode. Do I have a data dependency? Yes, for 4. Okay, well, 4 was updated all the way over here, right? This time it was a source, not a destination. So it was being used, but it wasn't changed. All I care about is when was the last time it was changed. That's all the way over here, T4, all the way in instruction 2. So I have to wait until instruction 2 finishes loading until I can do this. This means I cannot exec this until after this W finishes, all the way over here. So I'm going to stall all of this. Now, after that, right, I could do fetch, decode, exec. It is an R type, so I just do no ops, write back. Instruction 6. I also can fetch over here because, remember, it's attached to core 2, and instruction 2 is also there. So I do the fetch when it's decoding. And now I can't decode right now because what's happening is there's a stall going on that core. Remember, it's as if core 2 is its own pipeline. So it's as if this is happening right now. So I do a fetch. I can't do anything right now. There's a stall happening. I can't do anything right now. There's a stall happening. I can't decode until my exec stage is happening for the previous instruction. So stall, stall, decode. Okay, now that I'm finally free from those stalls, now I can see if there's data dependencies. 7, right? T7. When was the last time it was changed? Instruction 4. Instruction 4 does not finish writing back. Oops, I actually never finished that. That's supposed to be an M, right? It doesn't finish until over here. And there should be an N because that's no ops. That means I have to wait. I have to stall until you finish all the way over here. I cannot exec until here. So I stall literally 4 times until I can do that. Then at this point, right, I can simply do my no ops and write back because it's an R type. And at this point, I am done. So this, you could see it gets very hairy when you have a lot of dependencies going on. Now, again, this was super scalar. So there's 4 cores going on at the same time. And this was a no ops MIPS pipeline, meaning I used no ops and I also had a pipeline going on. That's why I was able to layer these guys. Otherwise, I would have had to wait for each of these to be over until I start the next instruction. So over here, this would not have happened until after this one finished completely. This would not have happened until after this one finished completely. So it's very important to know the differences between those, but otherwise superscalar is not too bad of a topic. Any questions before we move on to the last question of the night? Thankfully, we're finishing off with an easy one. Okay, so last part. Over here, we have three different programs happening, and we need to know the difference between multi-programming and single and uni-programming. And we need to know single versus multi-processing. So, process, when you hear the word process, you want to think of your CPU. This means that it has multiple cores. If it is multi-processed, multiple processors, single process, a single processor, right? And what do these multiple processors let us do? They let us have multiple programs or instructions at the same time. That's what we did on the previous question with the superscalar. We had 4 cores. We were able to handle 4 instructions at the same time. This takes it one step further with having completely different processors. So I can run completely different programs all at the same time. I can allocate one program. I could allocate, let's say, Spotify to core 1, to processor 1. I could allocate Safari to processor 2. I could allocate Google Chrome to processor 3. And here, that's what we're doing with these 3 programs. Now, then we also have the other piece of the puzzle, multi versus uni programming. This is dealing with your OS, your operating system. This allows you to actually program it to say, you are going to handle this program. You are going to handle that program. Therefore, in order to actually have this work, you need both multi-processing and multi-programming. If you do not have either, you cannot use this, you could say, superpower that we've done with superscalar. Therefore, it just becomes a normal scalar processor, which becomes inefficient. Think of it as like you need to have the newest iPhone, but you need to have the newest OS to work with it. You need the best hardware and you need the best software for things to work correctly. So, in a question like this, calculate the total number of clock cycles for the above executables on a single cycle, multi-programming, single processor system. I don't care that this is multi-programming. You just said it's single processor. I don't care. I could have the best OS in the world. I only have one processor. I can't use it. Because of that, right, I have to now do each of these individually. So let's find out how many cycles, right, I have to do for each of these guys. Well, program 1 is easy. This is just 1, 2, 3, 4. 4 instructions, 4 cycles. Boom. Okay? We're just doing clock cycles, so it's just the number of times that it takes to finish these, right? This is a single cycle, so that means each instruction takes 1 cycle to finish. Okay? Now we don't have to deal with branches, but now for program 2, we do. This is going to be 1, 2. Now, before I get into the loop, right? This is 3, 4, 5, 6, 7, 8. I know I have a loop over here. And this is telling me that I'm going to branch on less than when T7 is less than T4. Okay, T4 has the value 12, the value 12 in it, right? And each memory address contains 10, right? So that means load word T4 has a value of, 10 in it, right? It has mem address 12, and that's just defaults to 10. Okay? And we're going to take that and branch if T7 is less than T4. Okay, T7 is initialized at 0. Okay, so I first add T7, I add 1 to it. Okay, so I start out with 1. Okay, is T7 1 less than 4? T4, which is 10? Yes, we branch again. So this is happening once so far. I add 1 again. Okay? I'm ignoring this instruction and this instruction here. It's not really anything useful, so why bother going through it? Branch on less than is T7 to less than T4, 10. Yes. Okay, and we're going to keep going through this, right? We know that eventually this is going to keep happening, and this is going to essentially just keep looping and looping and looping. It's going to be a total of 1, 2, 3, 4, 10 times, right? So this is going to be a total of 10 times this loop is happening. And how many instructions are in here? 1, 2, 3, 4. So that's going to be 10 times 4 instructions plus how many leftovers? 1, 2 before, 1, 2 after, plus 4, 44. Okay, and then lastly, program 3. Okay, we're going to do 1, 2, 3, 4, 5. There's a branch here. This branch is saying branch on greater than if T7 is greater than 9. Well, we know T7 was initialized at 1 and it was not changed throughout. Therefore, 1 is definitely not bigger than 9. We don't continue through it. This is only 5. So this is 5, this is 44, and this is 4. So because this is not multi-programming and multi-processing, I have no choice but to do each of these one by one. So this is going to end up looking like this. It's going to end up looking like program 1, 4 cycles. Program 2, 44 cycles. Program 3, 5 cycles. So that's going to be a total of, add these guys up, and you're going to get a total of 53. That's for this case over here. Now, the second part, multiprocessing and multiprogramming. This with 2 processors. This allows us to actually take advantage of that. And with this, right, now I have 2 processors. So I can handle 2 of these things at the same time. I can do program 1 with 4, right? And then on my other processor, I can handle program 2, 44. Now we know program 1 is going to finish way earlier. So program 3 is going to also get on this processor. So this is going to finish at 9, but this is still going to keep going. But since we got rid of the easy processes first, right, that's going to allow us to essentially only need to take the largest finishing time. So this is still going to finish at only 44 now. That is our best case. So because I was able to multi-process, multi-program, I delegated. You two are going to go on processor 1. You are going to go on processor 2. So these are happening concurrently at the same time, which makes it much more efficient. Otherwise, remember it says best case and worst case. If this was not programmed efficiently, the worst case would have literally just been you have 2 processors, but you didn't use them for some strange reason. You put them all onto one. I don't know, maybe the OS was having a bad day that day and was not in the mood to be efficient. So the worst case would be the same as the previous, which would have been the single cycle multi-programming single processor. So we can see how much better it is when we stack things up, like how we did over here. Okay. And with that, I finished just on time, 9:59. Wow. So that is the end of the review, but if you have questions, please ask. And please fill out the feedback form. For the non-MIPS superscalar, so it works exactly the same. The only difference is just no no-ops, right? So if it's non-MIPS 5 stage, right, we're just not going to have the no ops in that case. But with superscalar, it's going to work exactly the same way. Okay, please fill out the feedback form, and thank you all for attending. This will be uploaded hopefully shortly. I also did a recording, so I'll also put it on my YouTube as well. So have a good night, everyone.
Have a good night, and thank you so much for the review.
Absolutely. Happy to
Goodbye.
help.
Good luck with your finals,
Thank you.
and Merry Christmas.